All right. Hello, everyone. Hope you all had restful enough weekends, all things considered. And I hope you're all doing all right, staying healthy. Good morning. Good morning. Today, the very first thing we're going to do is, after opening it up for you guys to ask questions, I want to talk just a tiny bit more about the last formula from Chapter 6, because I know it was a bit of a doozy, and there's at least one more example I'd like to do with you. And since we're covering that little piece today, as I said in the email I sent out yesterday, I'm extending the Chapter 5-6 assignments to be due this Thursday, just to give you a little more time to use whatever information you pick up today. So those are currently due Thursday. We are going to today also begin talking about Chapter 7. Chapter 7 is the introduction to heat and thermal energy, and it's just the introduction. So Chapter 7 itself is not very long or complicated, so I do foresee us being able to finish all of Chapter 7 this week. As such, the Chapter 7 assignments are presently due for next Tuesday. That includes the lab that I emailed out yesterday as well. And as a reminder, we are also on track. Good morning. Good morning. You're also on track to resume having our other class meetings next week. So for those who are able to make it in person, that will become, again, an option next Tuesday. So we are currently on schedule for things to go back to the way that we were operating, exerting all caution though. And so this week, we're going to do just the tiniest last bit of Chapter 6 and then do Chapter 7. Homework and quiz are already live. You have the lab for this week. The pre-recorded lecture, you have that as well. I sent out a video link to a Chapter 7 pre-recording, so you have that at your disposal. And I do recommend you watch it so that you can come to these calls and with any of your questions. But for right now, before we get into the one last use of this big formula at the end of Chapter 6, do any of you guys have any questions at all about any of the material that we've covered recently, any of the assignments, any specific things from you guys before we begin today? Okay. Any questions come up, please? If any questions come up at any time, please do let me know. Cut me off, put in the chat. We are going to, I ask that you turn your attention very quickly to the last couple slides of the Chapter 6 notes. I will share screen so that you know where you need to be. This is the very, very last parts of Chapter 6. We have covered every formula you need for Chapter 5-6, but that last formula was a big one. So I want to do at least one more sample with you guys. Yes?
You moved the homework to be due on Thursday, right? Homework and quiz for Chapters 5 and 6.
Correct. All 5 assignments, homework, quiz, and lab, are presently due this Thursday.
Okay, cool. Thank you.
You're welcome. Do be aware the Chapter 7 assignments are presently due next Tuesday. So just keep that in mind. So on the 5-6 notes, we talked about Bernoulli's equation, and we worked at least one example with it. Now, the main function of Bernoulli's equation is to show what is happening in a system before and after some sort of a pressure change, or comparing two different parts of a pressure system. The example that we looked at last time, which is currently the one that I'm screen sharing, this is slide number 6, was the Gatorade tank. And in that particular problem, there was 2 different regions where the fluid in question, the Gatorade, was under different amounts of pressure, undergoing different tasks. Different things were happening to it depending on where you were looking at it. The two spots we compared were what's happening to the Gatorade as it just sits in the bottom of the tank while the tank is closed versus what happens to the Gatorade as the nozzle is open and it begins pouring out. So this formula, the Bernoulli's equation, it is essentially a before state and an after state. Notice the two sides are the same. You're just comparing every element that adds pressure into a system before some change happens and comparing all of that to every same element after that change happens. And sometimes, excuse me, sometimes various elements on either side are going to cancel out. This long form of the equation exists to incorporate every possible thing that can affect pressure on either side. You have the natural pressure coming in from outside of the system. This represents air pressure. You have pressure from the fluid in question moving at some velocity. You have pressure due to some amount of fluid above the spot you're looking at. All of these can add to the pressure of the system, and we're examining them and comparing them before and after. Now, in the case of the Gatorade in the tank, if the initial spot is right here in the tank and we're not moving, this term would cancel out. Meanwhile, as the Gatorade exits the tank, now it's moving, but there's no longer any Gatorade above it. So you work with this type of a formula, with the Bernoulli's equation, very often things will cancel out on either side, and you don't have to do the entire thing every single time. Because it's very rarely that in a pressure system, every single thing changes from the 2 points that you're looking at. Now, this formula is very useful in very specific places. It can help us to explain why the Gatorade tank just doesn't pour out very quickly when it is empty. I'm sure you've dealt with the frustration of you want something from a tank like this, and when you open the nozzle, it barely pours out because the tank is almost empty. I'm certain that most people have dealt with that frustration before. I know that's kind of a niche use for this formula, but there's another specific application it has that even if you never do the math for it ever again, is at least useful to understand. And that is actually flight. When a bird or a plane is flying, it's the mechanism that allows something to basically glide through the air is due to changes in pressure between the top part of the wing and the bottom part of the wing. That's what we're going to look at now. Our last example is going to be looking at how flying works from the perspective of Bernoulli's equation. So if you move on to slide number 7, this will explain the example question. So you should be looking at slide 7. Whoops. Okay. So the first thing I'm going to draw is actually the wing shape, because the shape of the wing for anything that can fly is very important. Now, this picture is a wing from the side view. Obviously, if you were looking down from the top of the plane, the wing would look, if this was the plane from a top view, you'd see the entire length of the wing. But right now we're looking at this from the side. So if you need some added details to be able to understand what we're looking at here, we're looking at the plane from the side. So coming in from the side, this is the profile of the wing. And it is very specifically shaped kind of like a teardrop. It is flat on the bottom. It comes up and jumps up pretty high at the top. It is more curved on the top than it is on the bottom. The shape of this wing is very important. To read the example through, Bernoulli's equation can also help us explain flight. Let's assume a model plane is flying at a velocity of 25 meters per second. I'm running a little low on board space, so I'm going to actually erase our older formulas and start listing variables up on the left here. All right. So the plane is flying at 25 meters per second. The air flowing under the wing is then therefore moving at a velocity of 25 meters per second. So when anything flies through the air, it literally flies through the air. If the plane is moving forwards at 25 meters per second, that means it's passing the air beneath the wing at a rate of 25 meters per second. If you were looking at this from the air's perspective, you might say the plane is moving at 25 meters per second through the air. If you were looking at this from the plane's perspective, if you were on the plane, it might look and seem to you like instead of you moving, it might feel like the wind is moving past you at 25 meters per second. So the plane is moving forward at this velocity, but that also means that from the plane's perspective, this is also the velocity that the air is rushing past beneath the plane's wing. So this velocity we can use to assume what the velocity of the air under the wing is. So the air is flowing under the wing of the plane at 25 meters per second, but the wing's shape makes it so that air flowing over the top of the wing moves at a faster speed. So air moving beneath the bottom of the wing is going to have a speed of 25 meters per second. Air moving over the top of the wing will have a velocity of 30 meters per second. Now notice again, the bottom of the wing is flat. So as the wing moves through the air is just going to move under the wing at the same relative speed. So since the plane is moving at 25, wind will pass under the wing at 25 because the wing is not getting in its way to interrupt that. But notice, if air is going over the top of the wing, I'm actually going to draw in the air currents now to help visualize this. For air to go over the top of the wing, now it has to go around the whole thing. And that has the effect of making the air over the top of the wing faster. The wing pushes it out of the way, and it has to move faster over the top of the wing to keep pace with the wind under the wing. Since it had to move out of the way, it has to cover more space in the same amount of time. So for all objects that can fly, most of them, if it uses a wing in order to fly, this is ignoring things like a blimp or a hot air balloon. They don't use wings to fly. If they need a wing in order to fly, the wing shape is always such that air is going to be moving faster over the top of the wing. We're going to assume that this wing is narrow enough such that as the air moves up and over the wing, the height increase there is negligible. We did say that this is just a model airplane. That means its wings are probably very thin. As the air rises over the wing, it's not going to be a very big increase, so we're just going to disregard that change in height. Now, we know the two speeds of the wind over the wing, beneath the wing, 25 meters per second, over top of the wing, 30 meters per second. Now, standard atmospheric air pressure this is a constant that will be available to you whenever you need it. Standard atmospheric air pressure is 101,325 pascals. And so we can assume that that is the air pressure under the wing, because under the wing shape is not interfering with the wind passing at all. That air is just moving as it would normally. This basically under the wing is just normal air. And so we're giving it all the variables of the normal air here, which includes standard air pressure. So we can consider this to be the pressure under the wing. So 1 atmosphere, 101,325 pascals. It's going to be pressure on the bottom. We're also told that the air's density is 1 kilogram per meter cubed. So this is just the general density of air at sea level. This constant will also be made available to you if you need it. The thing we are asked to find with all of this information is, what is the air pressure on top of the wing? So we know the difference in velocity of the air on the top and bottom of the wing. We know the pressure on the bottom of the wing, air density. We want to know the air pressure on top of the wing. Now, it's easy to ask yourself, why would the pressure be any different? Because it's all still just air. But bear with me as we do this math, and I'll show you something cool about it. Our two states here, the two states we're going to be comparing, are beneath the wing and above the wing. So one side is going to be every variable beneath the wing. The other side is going to be every variable above the wing. So before we continue, we can make life a little bit easier on ourselves. We did say that this change in height from the bottom of the wing to the top of the wing is going to be negligible. It's not going, the air is not going to rise very high above the wing. It's not going to be a very regardless of top wing or bottom wing is going to be functionally the same, which means that these two terms on either side, the PGH terms, will be the same, because it's the same air density on both sides, it's the same 9.8 on both sides, and we're assuming that the height of the air above the wing will remain the same from beginning to end, which means these two terms are just going to cancel out, and we don't have to worry about them. Since it's the same on both sides, they just cancel away. That's two things we don't have to do any algebra for. So let's treat the left side as bottom of the wing and the right side as top of the wing. On the bottom of the wing, we've established that the air pressure on the bottom of the wing is just going to be normal air pressure. It's going to be 101,325 pascals plus density times velocity squared divided by 2. So the density of the air is 1, moving at a velocity of 25 meters per second under the wing, and divide that by 2. So that's our left side. That's everything going on beneath the wing. On the right side, we want to solve for what the pressure is above the wing. And we know air density times velocity on top of the wing. We need to square these velocities. Divided by 2. And now to fish my calculator out of the bottom of my backpack. All right, so we're just going to simplify this by one line. We're going to take the two velocity terms and turn them into single numbers to help us solve for P2. 1 times 25 squared divided by 2 is 312.5 equals P2 plus 1 times 30 squared divided by 2, which is 450. So we're going to end with an answer that says that the pressure beneath the wing should come out to be 101,187.5 pascals. Now, the pressure beneath the wing is 101,325. The pressure is lower on top of the wing. Pressure is lower on top of the wing. And so ultimately, what's going to happen here is very similar to what we discussed when an object is floating in water. When you submerge an object, a solid object, in a fluid, it's surrounded on all sides by fluid, and it's going to exert a pressure inwards in all directions. But the bottom of the object, since there's more pressure the deeper you go, there's more force pushing inwards at the bottom than there is at the top, which has a net effect of the buoyant force pushing upwards. It's the same thing here. We just discovered that the pressure on the top of the wing is lower than the pressure on the bottom of the wing. The pressure on the top is going to push into the wing downwards. The pressure on the bottom is going to press into the wing upwards. There's more pressure on the bottom, and that means the net amount of pressure, the net force acting on the area of the wing is going to point up. Flying is basically literally floating in air. It's still a buoyant effect, but it comes about due to the shape of the wing as it moves through the air. And the plane does have to be moving for this to work. If the velocities were 0, then the pressure wouldn't be any different on the top or the bottom. When the plane is just sitting still in the hangar and not moving, there's no air moving past the wing, so there's no difference in pressure. This pressure difference is caused by the principles we noted before. Basically, when the velocity because it's the difference in velocity from the top and bottom of the wing that creates this change. You need the air to move faster over the top of the wing because that's going to be what creates that lower pressure on the top that lifts the plane upwards. So this formula, Bernoulli's equation, is the principle that allows planes to fly, among some other things. If you move on to slide 8, there's other places that this does come into effect. It specifically says, as an example, gophers, which is not a case I knew about until my professor told me how Bernoulli's equation comes into play there. But what gophers will do digging their dens is they'll create 2 entrances into their underground nests. And they will always make sure that one of those entrances is lower than the other, so that when wind blows past the den, they're at different heights. The wind is going to be moving at different speeds for each part. That's going to have the net effect of a pressure difference between each side of the gopher hole, which is going to cause air to move through the gopher hole, ventilating it, which is not a thing I ever knew about. And it proves that gophers are smarter than you'd think they are, because they understand this principle well enough to build their dens this way, which I think is pretty cool. This might seem like an incredibly niche formula, but it does show up surprisingly often in nature, in industry, and in life in general. I know it's still kind of long, might still look intimidating, so again, I remind you, as you are working on your assignments, at any time you have a question, I know I say this 1,000,000 times, I know it probably gets old, but I honestly feel like sometimes people need a reminder that you can ask me stuff, because when I was giving you guys the test, not many people actually stopped in the middle of the test to ask me a question. If you don't have any, I don't want to pressure you, but if you do have any at any time, it's always an option. So that Bernoulli's equation wraps up chapter 5, 6 combined. And so with this information, please go on and continue to be working on finishing up those materials this week. Before we switch gears today, I'll give you guys a chance to ask any questions you have, any things that you've noticed as working through the assignments, any issues you've had with the material, or questions about this week in general. Okay, if there's no questions, we're going to switch gears and start looking at chapter 7. This is our new material for this week. And this chunk of the class, I've been saying that the class is sort of divided into 3 separate chunks. The first chunk, move in our universe. This chunk that we're in now, we've been looking at pressure systems. It's not just going to be about pressure. We're also going to now begin talking about heat and thermodynamics, which actually does connect very strongly to pressure systems, because very often the pressure that a fluid exerts depends upon its thermal state. So we're going to begin discussing what thermal energy is, what it does, what we use it for this week, and next week we're going to sort of combine pressure and thermal energy together to examine why they're so interconnected. So this week is going to be chapter 7. Next week is going to be chapter 8. which means that once we've finished chapters 5 through 8, we will have completed the next chunk of the class, the next sort of core. That means that we will have another test on the horizon. It's not going to be for about 2 or so weeks, so don't worry. I just want to make you aware test 2 is coming. I would anticipate it being perhaps I'd probably make it available towards the tail end of the first week of November, maybe the beginning of the second week of November. So announcement here and now, test 2 is coming in the next couple of weeks. We've got chapter 7 this week, chapter 8 next week, and then we'll spend time reviewing the week after that to tie all of this chapter 5 and 6, 5 through 8 together before test 2. We'll talk more about that as we get closer to it. Just, it is on the horizon. It is approaching. Do not be alarmed. But now let's talk more about chapter 7 itself. I do recommend you have the chapter 7 notes open. They are both on the Brightspace page and also in the email I sent out yesterday. I'm just going to screen share so that you know what you should be seeing. So, chapter 7 is about thermal physics, and that is what the title slide says. So make sure that you are looking at the right set of notes. And thermal physics is going to refer to the understanding of heat and thermal energy, how it's created, what it does, how it moves, and what happens to objects when they possess thermal energy. So if you can see this title slide, you are in the right place. Slide 2, we begin at forms of talking about energy itself. So we have talked about energy. We defined energy previously as it is a thing that matter can possess. It's not a very good definition of energy, but that is the best way that we can understand it. Energy itself, we cannot see the energy, but we know that objects can have energy and then do things with that energy. The two forms of energy we looked at before, kinetic and gravitational potential, those are both forms of mechanical energy. Energy can't be created or destroyed, but it can take on a lot of different forms. And very often when energy transfers between objects, it's going to change its state in some way. That statement beneath the title of this slide, energy cannot be created or destroyed. That is a very specific law of physics that we call the law of conservation of energy. You cannot create new energy and you cannot destroy old energy. Whenever you use energy up, it just goes somewhere and takes on another form. And if energy is not in an observable mechanical form, like the two that we've talked about, then odds are it has been used up and is now in a non-mechanical form, like thermal energy. Whenever you use up energy in a task, whenever you do work and use your energy to accomplish something, the energy you used in that process gets turned into a different form of energy and transferred into a different place. And pretty much every single physical act in the universe, every time something moves, every amount of energy used up in some physical process is going to create some amount of thermal energy. So even though energy cannot be destroyed, you can turn it into thermal energy. And once it is thermal energy, it tends to stay that way. So moving on to slide 3. What thermal energy is, again, we can only tell when energy exists when we can observe an object possessing thermal energy or any type of energy. When you see an object that has kinetic energy, you know it has kinetic energy because it is moving. An object, you can observe an object having gravitational potential energy because it is some height above some other point and can fall to that point. An object has electrical energy if there is electric current running through it. An object has chemical energy if it has chemical bonds that can be broken down to release that energy, like your food. An object with thermal energy shows that energy by having its molecules and its atoms begin moving. Thermal energy, the word thermal means of or referring to heat and temperature. So thermal energy is the energy that makes things warmer. And I did say a second ago that every single physical act cause some amount of energy to become thermal energy. The easiest way for you to observe this yourself is just to take your two hands and one another. And the first thing you should pretty quickly notice is that your hands are going to start to feel warmer. The reason for this is when you drag your hands across one another, there's friction between your palms. Friction has a tendency to take energy away from a system. Friction is designed to slow things down and make them not move. Friction will take energy away out of the kinetic state of my hands, because if I'm moving my hands, they have kinetic energy. Friction will take energy away from the kinetic state and transform it into thermal energy. All friction creates thermal energy, which is why when you drag anything across anything else, it tends to be warmer. Like when you slam on the brakes in your car, usually your tires and the road will warm up as your tires skid across the road because there's friction between the tires and the road. And that friction takes kinetic energy away from your car. You are slowing down, so you have less kinetic energy, and just turns it into thermal energy, which just has the effect of making everything around it warmer. So on the atomic level, what happens when objects possess thermal energy is their particles start to move around more. We talked about the states of matter before, solid, liquid, gas, and plasma. And we noted that the differences between the states of matter have partially to do with how fast their particles are moving and how far apart they are. When you heat anything up, when you add thermal energy into an object, its particles begin moving around more, bouncing off of each other, and eventually sort of spacing farther apart. If you can see the images on slide 3 that show this, there's one diagram for hotter and one diagram for colder. The hotter something is, the more thermal energy its particles have, the more its particles are moving. That has a tendency for them to bounce off of each other and naturally space themselves apart. The colder something is, meanwhile, the less its particles are moving, the less energy they have, and they're slower, they're not bouncing off of each other as much, they tend to sit closer together. This is why when you heat something up, it will eventually melt and eventually evaporate. The more thermal energy you add to an object, the more its particles bounce off of each other, the farther apart they tend to drift. Eventually, an object's particles drift so far apart, it creates a phase change. And this is why when you go from solid to liquid, the particles get farther apart and the object becomes a lot looser and more fluid. And then as you heat it from a liquid to a gas, its particles get even farther apart and it just evaporates into gaseous form. So thermal energy takes the form of making the particles that possess it move. And because atoms have mass, when they possess thermal energy and they are moving, you can think of thermal energy as a kind of atomic level kinetic energy. It is making particles with mass move and bounce off of one another. So it is a type of mechanical, it is energy, but because it cannot perform, you cannot perform mechanical tasks with just thermal energy by itself. Just having thermal energy won't always accomplish anything. You can't get mechanical work out of just thermal energy by itself. We don't tend to think of thermal energy as a form of mechanical energy, but it does make things move on the atomic level. If you move on to slide 4, very similar drawing to the last one. It shows the collisions involved between hot and cold objects. The faster the particles move in an object, the more times its particles are going to collide, and that has a tendency to end up spacing them out. Moving on to slide number 5. Collisions between particles result in work being done in terms of one particle bouncing off of another. If you remember when we were talking about collisions a couple of chapters ago, when one object collides with another, you're going to trade momentum between those two objects, and kinetic energy might transfer between those two objects. When atoms, the atoms that make up every single object, when those atoms collide, they are going to trade energy back and forth as well. Pretty much all atoms have elastic collisions. So when one atom hits another one, energy is going to transfer from one to the other, and they're going to bounce off of one another. In doing so, you can transfer thermal energy from one atom to another by allowing the two atoms to collide. This process is what allows thermal energy to transfer between two different objects. So let's say we are looking at two separate objects, my hand and my calculator. Let's just say my calculator is like the whiteboard. It's a vertical surface that you can put your hand on. And let's say that my hand is very, very warm and the calculator is very, very cold. That means that I have a lot of thermal energy in my palm, and the particles that make up my palm are bouncing off of each other and moving around very quickly. If the calculator is colder than my hand, it doesn't have as much thermal energy, and its particles are not bouncing around very fast. But when I take my hand and I touch the calculator, the particles that make up my hand are then able to collide with the particles that make up the calculator. And in the collisions between my atoms and the calculator's atoms, energy will transfer from my hand into the calculator. When two objects are touching and thermal energy can transfer between them, we refer to that state as thermal contact. So when you touch anything, that is a state of thermal contact. It is direct contact with an object that can give you or take away from you thermal energy. And when you touch anything and you feel warmth, if you touch something that is warmer than you and you feel that warmth, when you touch that object, you are then in a state of thermal contact, and the particles that make up your hand collide with the particles that make up the object you're touching. And if you feel warmth, that means you are touching an object that has more thermal energy, and in the collisions between your particles and that object's particles, thermal energy is going to end up transferring into your particles and into your body. So the sensation of warmth represents heat transfer through contact into your body. Meanwhile, if you touch something that is colder than you, you have more thermal energy than it. And in those collisions, thermal energy will end up transferring out of your hand and into the other object. That is the sensation of cold. Cold, when you feel cold, that is thermal energy leaving your body. Which means that in general, coldness is not its own unique thing. You cannot look at, there's not a specific type of energy that if you add this energy to something, that makes it more cold. Cold is actually the absence of heat. Thermal energy is what makes things warm. If you have thermal energy, you're warm. If you don't have thermal energy, you are cold. And when you feel cold, you are losing thermal energy through thermal contact. This describes, if you move on to slide 6, this describes heat transfer, which is what we're going to start talking. This is where it's at 10:50 now, so this is the end of the period. So we've talked about what thermal energy is, and next time we're going to pick up looking at how it transfers between objects, the ways that it transfers, and start doing some of the math for that. So that is the beginning of Chapter 7 for you guys. The Chapter 7 assignments are now live. I do recommend you begin looking. I'll have office hours at 1:30. If you have any questions now before you go, please feel free to stick around and ask. But if you have to get to class, or if you have anything else you need to be working on, thank you guys very much, and I hope you have a wonderful day.
Oh, I had a question about the lab.
Yes, sure, go ahead.
It's about like when they talk about what's the physical meaning of the slope.
Yes.
And so like I just put like the greater the depth, the more pressure is added. So like I was
Okay,
like,
yes.
the farther you go down, the more pressure is on you.
Mm-hmm.
So that's good. We can use that. That's basically what the slope means, right?
That is a summary of it. Since you graphed depth on the x-axis, the slope represents some quantity that you multiply by your depth to create the amount of pressure that is added at that depth. So yes, the deeper you go, the more the pressure is, and the slope represents how much that increases.
Okay. And like what do they mean by what's the physical meaning of the y-intercept? What is that?
Well, depending on how you input your numbers, if you look at the number that is the y-intercept, just at the number itself, it should look familiar. It should look like a number we've used a few times if you put your numbers in correctly. If you put your numbers into the system correctly. Can you tell me what number you got for the y-intercept?
Oh, I gotta pull that. Like the number is adding by.
Yes.
Mine says 95,203.
Okay. That's not exactly the number I was looking for, but it is close in value to the number I'm thinking of. Is there any number that's shown up a couple of times this last week that is at least close to that number?
I'm talking about like that we've done, or that's
Yes.
one.
A number that has shown up in multiple problems. It's a constant that shows up pretty often.
We must be don't have. Oh, shit. This ain't one of these. Word. I can't find it. I don't know. Something.
Excuse me.
So it's like a constant number and a formula or something that we use.
Yes. Okay, so your graph along your x-axis, you graphed from you should have put your numbers in from starting from a depth of 0, like 0 meters into the water, then half a meter, and then a meter in the water, etc. So the y-intercept tells you what the pressure should have been at a depth of 0 meters into the water. So you're not any depth into the water yet. That means none of the pressure present came from the water at that depth. So if you're not in the water yet, where is that pressure coming from?
Oh, from gravity?
You're getting there. Gravity doesn't exert a pressure directly, but there is something that is currently exerting pressure on you right now.
Oh, the Earth. Oh, the Earth. It's the Earth, or is it something? Because it's like 101 something.
Yes, very good. What does that number mean? The 101,325.
The amount of pressure that's on every human being, like.
Right, but from what?
Oh, I wrote that down. I got that somewhere. The atmosphere?
Yes, that's the atmospheric air pressure. That number represents the pressure from the air before you ever got in the water.
So that's basically what the y-intercept means.
Yep, that's what it represents. It's the pressure from the air that existed before you got in the water. And that means every inch you go deeper into the water, you add pressure from the water, and all that air pressure above you is still there.
And then, like, I got a question about the other simulator for buoyancy.
Okay.
It's the number 6. It's that long question. It says, you place the wood block in the water and notice that it floats. And when the wood block rests on the ground, the downward gravitational force is balanced by an upward normal force. And when floating, the gravitational force is still there, but the normal force is not. And the force exerted by the fluid is the buoyant force. When floating, which force is greater, the gravitational force or the buoyant force? Defend your answer.
Oh, okay. So I'm actually going to pull up the simulation to show it with you. Okay. So I've got the simulator loaded right now, and by default, the system shows you the mass of every single object. It shows you the liters in the pool. It shows you the newtons, the weight of whatever you put on the scales. But in the bottom left of the screen, there's already a check mark saying that there's a mass readout. But you can also turn on force values. You turn on readouts for force values, and then hit all of these arrows here to show the different kinds of forces acting upon an object. So got it showing arrows for a So if I release it, the only force points down and it'll fall. But when I drop it into the pool, it takes a second, but eventually everything's going to balance out. Notice the force of gravity down reads 49 newtons, and the buoyant force upwards also reads 49 newtons. And then if I put it back on land, now the arrow is orange. That means it's the contact/normal force instead. Those two forces equal out here. I'm going to make the object float again, and the buoyant force was equal to the force of gravity. So in the simulator, you can turn these arrows on to show you what the force values present are.
So basically, my answer would be that they're the same value.
Yes.
The forces are equal.
Right. For anything to float,
the forces have to be equal.
Yes. If I push this below the water surface, the buoyant force is larger, which means if I let go, it's going to rocket to the surface until eventually things even out again. Notice that the bricks sink. The bricks aren't floating. The bricks sank. And its buoyant force is not as much as gravity, so it just sank to the bottom.
And so,
sorry, say again.
When it says like record the value of the buoyant force acting on the wood, you're just getting that from the simulator, right? So you just put the 49.
Yes.
And then like, because I just really want to know, like, because it was saying how to record all this stuff, and I was trying to figure out like how to set it up to where I can get those answers.
Okay, I'm sorry. Yes, I know you might not be able to see my mouse cursor right now, but it's these check. Oh, you can? Okay,
yeah.
Good. I've had students who just couldn't see it in the past. If you turn on these check boxes on the bottom left, it turns on all the options to see the arrows and the numbers.
Thank you.
You're very welcome. Have a good day, guys.